You've been taught a lie about how Earth moves through space. Most people think our planet simply orbits a stationary sun, but the reality is far more extraordinary. Our entire solar system is actually racing through the Milky Way at over 220 kilometers per second, creating a massive helical spiral pattern that scientists continue to refine with new measurements. Recent velocity updates from projects like the Vera catalog have confirmed we're moving even faster than previously calculated. And here's what makes this movement significant. These orbital patterns connect to long-term cycles that may influence everything from climate changes to major environmental shifts throughout Earth's history. But to understand why this matters, we first need to grasp a fundamental principle about motion itself, the airplane analogy that changes everything. Picture yourself sitting in a commercial airliner cruising at 35,000 feet. You're sipping coffee, reading a book, maybe watching a movie on your screen. Nothing around you suggests you're racing through the atmosphere at 900 kilometers per hour. The flight attendant walks down the aisle normally. Your drink sits perfectly still on the tray table. From your perspective inside that aircraft, you might as well be completely motionless. This simple observation reveals one of the most profound principles in physics, and it's the key to understanding how motion works throughout the universe. What you experience in that airplane cabin represents Galilean relativity in action. This principle, first described by Galileo Galilei in the early 1600s, explains that uniform motion is completely relative to your frame of reference. Inside the aircraft, you and everything around you share the same motion, so you can't detect it. The only way to know you're moving is to look outside and see the ground rushing past below. But here's where it gets interesting. That person standing on the ground, watching your plane fly overhead, perceives your motion clearly, while from their perspective, they remain perfectly still. Neither viewpoint is wrong. Both are valid frames of reference. This relativity principle becomes mind-bending when we apply it to our cosmic situation. Right now, as you sit reading this, you feel completely stationary. Your coffee cup sits motionless on your desk. Your houseplants aren't flying around the room. Everything appears perfectly still, just like inside that airplane. But this perception represents only one frame of reference, and it's hiding the most spectacular truth about our existence. The reality is that you're currently traveling through space at speeds that would make that 900 kilometer per hour airplane seem like it's crawling. Earth rotates on its axis at roughly 1,670 kilometers per hour at the equator. Simultaneously, our planet orbits the sun at an average speed of 107,000 kilometers per hour. But these numbers barely scratch the surface of our true cosmic velocity. Recent measurements from Japan's Vera project show our entire solar system races through the Milky Way galaxy at approximately 227 kilometers per second. Yet you feel none of this motion because you're sharing the same reference frame as everything around you. Most people learn about planetary motion by focusing on Earth's orbit around the sun, treating the sun as a fixed point in space. This perspective made sense for early astronomers trying to understand the basics of celestial mechanics. However, choosing this limited frame of reference creates an incomplete picture of reality. It's like trying to understand the airplane's journey by only observing the movement of passengers within the cabin while ignoring the fact that the entire aircraft is flying across continents. When we expand our frame of reference to include the galaxy itself, everything changes. The sun, which appears stationary from our earthbound perspective, becomes a moving object carrying its entire family of planets, asteroids, and comets along for the ride. This shift in perspective transforms our understanding of planetary motion from simple circular orbits to something far more complex and beautiful. Instead of Earth tracing the same circular path around a fixed sun year after year, our planet actually follows a helical spiral pattern through three-dimensional space. Think of it this way. If you were to track the path of a passenger walking down the aisle of that flying airplane, their movement would appear as a straight line from your perspective inside the aircraft. But someone observing from outside would see that passenger's true path as a complex curve through space, combining their walking motion with the airplane's forward velocity. Earth's movement works similarly. From our solar system's perspective, Earth orbits in what appears to be a closed loop. But from the galaxy's perspective, Earth never returns to the same point in space. Instead, it spirals forward through the cosmos, creating a helical path that stretches across billions of kilometers. This expanded perspective reveals that our solar system functions more like a cosmic locomotive than a static arrangement of orbiting planets. The Sun acts as the engine, pulling all the planets along as it races through the galaxy. Each planet's orbital motion gets combined with this tremendous galactic velocity, creating individual helical trajectories that weave through space in a magnificent cosmic dance. Understanding our true reference frame becomes crucial when we consider the consequences of this movement. As our solar system travels through different regions of the galaxy, it encounters varying densities of cosmic dust, different levels of radiation, and gravitational influences from nearby stars and stellar remnants. These environmental changes can have profound effects on our planet's climate, magnetic field, and even the evolution of life itself. Recent astronomical discoveries have shown that our solar system's path through the galaxy isn't random wandering. We follow a specific orbit around the galactic center, and this orbit includes vertical oscillations that carry us above and below the galaxy's main disk. These oscillations expose Earth to different cosmic environments on predictable timescales, potentially explaining some of the cyclical patterns scientists observe in geological and biological records. The choice of reference frame also affects how we interpret cosmic phenomena. Many astronomical observations that seemed mysterious when viewed from Earth's perspective make perfect sense when considered from the galactic reference frame. The apparent motion of nearby stars, the distribution of cosmic ray particles, and even the structure of our local stellar neighborhood all become clearer when we account for our solar system's true motion through space. But even this galactic perspective reveals only part of the story. To truly understand Earth's movement, we need to examine the details of our planet's path around the Sun itself, which turns out to be far more intricate than most people realize. Earth's elliptical dance, the 2025 Precision Update. Most people picture Earth traveling around the Sun in a perfect circle, like a marble rolling around the rim of a bowl. This mental image feels comfortable and predictable, but it represents a fundamental misunderstanding of our planet's actual path through space. Earth's orbit forms an ellipse, not a circle, which means our distance from the Sun changes dramatically throughout the year. This seemingly simple detail creates consequences that ripple through every aspect of life on our planet. NASA and ESA missions, including spacecraft tracking systems and the Gaia Observatory, have refined our measurements of these orbital variations to within just a few kilometers. These calculations reveal that our planet follows an elliptical path where the Sun occupies one focal point, not the center. At our closest approach, called perihelion, Earth sits approximately 147.1 million kilometers from the Sun. At our most distant point, known as aphelion, we drift out to roughly 152.1 million kilometers away. The difference between Earth's closest and farthest positions from the Sun spans over 5 million kilometers. To put this distance in perspective, you could fit more than 390 Earth-sized planets in the gap between our perihelion and aphelion positions. This variation of 3.4% in our solar distance translates into significant changes in the amount of solar energy reaching our planet throughout the year. The timing of these orbital extremes creates effects that scientists continue to investigate. Earth reaches perihelion around January 3rd each year during the Northern Hemisphere's winter. Conversely, we reach aphelion around July 4th in the middle of the Northern Hemisphere's summer. This timing means that Earth actually receives about 6.8% more solar radiation in January compared to July. The Southern Hemisphere experiences the opposite pattern, receiving its maximum solar input during its summer months when Earth sits closest to the Sun. Advanced climate monitoring satellites can now detect subtle changes in atmospheric temperature, ocean currents, and ice sheet behavior that correlate with our changing distance from the Sun. These measurements reveal that the elliptical orbit affects global weather patterns in ways that were impossible to detect with ground-based instruments alone. The gravitational dance between Earth and other planets adds another layer of complexity to our orbital motion. Jupiter and Saturn, the solar system's giant planets, exert gravitational forces that slowly modify Earth's elliptical path over time. These planetary influences cause what astronomers call perturbations, which gradually change the shape and orientation of our orbit across thousands of years. When Jupiter and Saturn align in their respective orbits, their combined gravitational pull creates measurable effects. Throughout the entire solar system, current research shows that Earth's orbital eccentricity fluctuates in predictable cycles spanning approximately 100,000 years. Right now, our orbit is slowly becoming more circular, approaching its least elliptical configuration in this long-term cycle. However, this gradual change occurs so slowly that human civilization has never experienced the more extreme orbital variations that occurred in Earth's distant past. During periods of maximum orbital eccentricity, the difference between perihelion and aphelion distances becomes much more pronounced. At these times, Earth receives up to 23% more solar radiation at its closest approach compared to its farthest point from the Sun. These dramatic variations in solar input have contributed to major climate shifts throughout Earth's geological history, including the advance and retreat of massive ice sheets during glacial periods. The elliptical orbit also affects Earth's orbital velocity in accordance with Kepler's laws of planetary motion. When our planet approaches perihelion, it moves faster in its orbit to conserve angular momentum. During aphelion, Earth travels more slowly. This changing orbital speed means that the time Earth spins in different portions of its elliptical path varies throughout the year. The northern hemisphere's winter occurs during the faster portion of Earth's orbit, making northern winters slightly shorter than northern summers. Modern computer models incorporate these orbital variations with remarkable precision. Climate scientists use current orbital data to understand how past changes in Earth's elliptical path contributed to ice age cycles and other long-term climate patterns. These models also help predict how future orbital changes might influence global climate, although such changes occur over timescales far longer than human history. The gravitational influences from other planets create additional orbital complexities that recent research has begun to quantify with new accuracy. Mars, Venus, and the Moon all exert small but measurable gravitational effects on Earth's orbit. Even distant Uranus and Neptune contribute tiny perturbations that accumulate over millions of years. These combined influences mean that Earth's orbital parameters undergo constant, subtle modifications that affect our planet's long-term climate evolution. The precision of current orbital measurements has also improved our ability to predict future astronomical events. Scientists can now calculate the exact timing of perihelion and aphelion passages decades into the future, enabling more accurate climate modeling and agricultural planning. This enhanced understanding of Earth's orbital mechanics provides crucial data for space mission planning, as spacecraft trajectories must account for our planet's changing position and velocity throughout its elliptical path. Yet this elliptical dance around the Sun represents only one component of Earth's true motion through space. While our planet traces its annual elliptical path, something even more surprising occurs within our solar system itself. The gravitational relationships that govern planetary motion create unexpected movements that challenge our basic assumptions about how celestial bodies behave. The solar system's hidden wobble. The Sun itself moves in response to these gravitational forces, creating a wobbling motion that affects our entire solar system's path through space. When you picture the solar system, you probably imagine planets orbiting around a perfectly stationary sun that sits motionless at the center like a cosmic lighthouse. This mental image appears in textbooks, planetarium shows, and educational videos everywhere. However, this representation misses a crucial detail that fundamentally changes how we understand planetary motion. The sun doesn't remain fixed in space while planets dance around it. Instead, our star constantly moves in response to gravitational forces from the planets themselves, creating a complex wobbling motion that affects the entire solar system's journey through space. Jupiter, the largest planet in our solar system, possesses such enormous mass that it exerts a gravitational pull strong enough to move the Sun. This isn't a gentle nudge or minor influence. Jupiter's gravitational force actually causes the Sun to orbit around a point located outside the Sun's own surface. This gravitational interaction creates what astronomers call barycentric motion, where both the Sun and Jupiter orbit around their common center of mass, known as the barycenter. Vera and Gaia astrometry missions have provided precise measurements of this solar wobble using advanced space-based observations. Scientists can now track the Sun's position relative to distant background stars with extraordinary precision, showing that our star moves in a complex pattern influenced by multiple planets simultaneously. These measurements demonstrate that the Sun travels in an intricate path that combines influences from Jupiter, Saturn, and the other giant planets. The resulting motion creates a multi-layered wobble that changes the Sun's position by hundreds of thousands of kilometers over the course of several years. Saturn adds another significant gravitational influence to this cosmic dance. When Jupiter and Saturn align in their orbits, their combined gravitational effects create even more pronounced movements in the Sun's position. These planetary alignments occur regularly, creating predictable patterns in the Sun's wobbling motion. Jupiter and Saturn shift the Sun's position by about one solar radius, carrying planets in a shared wobble that fundamentally alters the gravitational center of our entire solar system. These observations reveal that the Sun's movement follows complex patterns that repeat over multiple decades. The wobbling motion shows clear correlations with the orbital periods of the giant planets, confirming that planetary gravitational forces drive these solar movements. This wobbling motion has profound implications for understanding our solar system's path through the galaxy. As the Sun moves in response to planetary gravitational forces, it carries all the planets along with it on this shifting trajectory. The entire solar system's helical path through space becomes influenced by these internal gravitational dynamics. Instead of following a smooth spiral through the galaxy, our solar system actually traces a more complex pattern that reflects the Sun's internal wobbling motion. The gravitational interactions extend beyond just the Sun and giant planets. Mars, Venus, Earth, and even the smaller rocky planets contribute their own gravitational influences to the system's overall dynamics. While these contributions are much smaller than those from Jupiter and Saturn, they add additional layers of complexity to the Sun's movement. These smaller gravitational effects accumulate over time, creating subtle but measurable changes in the solar system's trajectory through space. What appears as simple planetary orbits from our Earth-based perspective actually represents an intricate gravitational choreography involving every object in the solar system. Each planet influences every other planet, and all planets collectively influence the Sun's position and movement. This creates a dynamic system where gravitational forces constantly adjust and readjust the positions and velocities of all solar system objects. The apparently stable orbits we observe are actually the result of these complex gravitational interactions reaching a dynamic equilibrium. These gravitational dances become even more fascinating when we consider how they compound as the entire system moves through space at galactic speeds. The Sun's wobbling motion gets superimposed onto its high-speed journey around the galactic center. This means that the solar system's path through the galaxy includes not just a large-scale spiral motion, but also smaller-scale variations caused by internal gravitational dynamics. The resulting trajectory becomes a spiral within a spiral, creating an incredibly complex three-dimensional path through space. The internal motion within our solar system creates patterns that affect our galactic journey in unexpected ways. As the Sun wobbles in response to planetary gravitational forces, it changes the solar system's orientation relative to nearby stars and galactic structures. These orientation changes can influence how our solar system encounters cosmic dust, stellar winds, and radiation from other astronomical objects. The timing of these encounters depends partly on the internal gravitational dynamics that cause the Sun's wobbling motion. Recent studies have identified correlations between the Sun's barycentric motion and various astronomical phenomena. The wobbling motion affects the solar system's magnetic field structure and its interaction with the interstellar medium. As our system moves through different regions of space, the Sun's changing position influences how effectively the solar magnetic field deflects cosmic rays and other high-energy particles from reaching the inner planets. The revelation that Jupiter pulls the sun so strongly that our star actually orbits a point outside its own surface fundamentally changes how we perceive our cosmic neighborhood. The sun, which appears so dominant and central from our perspective, actually participates in a gravitational partnership with its planets. This partnership creates a dynamic system where the gravitational center constantly shifts based on planetary positions and alignments. Our entire solar system becomes a complex gravitational ballet where every participant influences the dance, contributing to the intricate helical pattern we trace through the galaxy. These internal dynamics create subtle variations in our orbital patterns that accumulate over vast timescales, potentially influencing Earth's long-term environmental cycles in ways scientists are only beginning to understand. Milankovitch cycles and the Ice Age connection. Among the most significant patterns emerging from this orbital complexity are the climate cycles first identified by Serbian mathematician Milutin Milankovitch. These cycles reveal how subtle changes in Earth's orbital parameters create profound effects on our planet's climate over thousands of years. Milankovitch identified three primary orbital variations that influence Earth's climate: changes in orbital eccentricity, axial tilt, and axial precession. Each operates on different timescales and creates complex interactions that drive long-term climate patterns. The eccentricity cycle determines how elliptical Earth's orbit becomes over approximately 100,000 years. When our orbit becomes more elongated, the variation in solar radiation between perihelion and aphelion increases dramatically. During periods of maximum orbital eccentricity, Earth receives up to 23% more solar radiation at its closest approach compared to its farthest point from the Sun. These extreme variations in solar input can amplify seasonal climate differences and contribute to transitions between glacial and interglacial periods. The obliquity cycle controls variations in Earth's axial tilt over roughly 41,000 years. Current measurements show that our planet's tilt ranges between 22.1 and 24.5 degrees, and this variation creates profound differences in how solar radiation reaches different parts of Earth's surface. Earth's tilt is gradually decreasing, moving toward the lower end of its range. This decreasing obliquity creates milder seasonal contrasts and promotes an overall cooling trend across the planet. The reduced tilt means that high-latitude regions receive less intense summer radiation, preventing complete melting of winter snow and ice accumulation. The precession cycle affects the timing of seasons relative to Earth's orbital position, completing its pattern over about 25,700 years. This wobbling motion of Earth's axis changes which hemisphere receives more intense solar radiation during different seasons. Currently, the northern hemisphere experiences winter during perihelion, when Earth sits closest to the Sun. However, precession gradually shifts this timing, creating cyclical changes in seasonal intensity that interact with the other orbital variations. These three cycles combine to create the complex climate patterns observed in Earth's geological record. The 100,000-year eccentricity cycle has become particularly prominent in recent Ice Age patterns, though scientists continue to debate why this cycle gained dominance over the shorter obliquity and precession cycles during the past million years. The transition to 100,000-year pacing in Ice Age cycles represents one of the most significant changes in Earth's climate system, and researchers are still working to understand the mechanisms that caused this shift. Advanced climate modeling now incorporates precise measurements of Earth's orbital parameters with unprecedented accuracy. Scientists can track changes in Earth's axial tilt with precision measured in arcseconds, revealing subtle variations that translate into significant climate effects over thousands of years. These measurements show that orbital influences on climate operate through complex feedback mechanisms involving ice sheets, ocean circulation, and atmospheric composition. Computational models can now predict future Ice Age cycles based on orbital mechanics with remarkable precision. These calculations show that the next natural Ice Age cycle should begin in approximately 50,000 years, assuming no other factors intervene. However, current atmospheric carbon dioxide levels may delay or prevent this natural cooling cycle. The enhanced greenhouse effect from human activities could override the orbital cooling influences that would normally trigger ice sheet expansion. The interaction between natural orbital cycles and human climate impact creates unprecedented complexity in climate prediction. While Milankovitch cycles have controlled Earth's long-term climate patterns for millions of years, the rapid increase in greenhouse gas concentrations over the past century introduces variables that didn't exist during previous orbital cycles. Climate scientists must now account for both natural orbital influences and anthropogenic factors when modeling future climate scenarios. Recent discoveries reveal that these orbital cycles themselves may be influenced by our solar system's movement through the galaxy. As our solar system travels through different galactic environments, it encounters varying gravitational influences from nearby stars and stellar clusters. These external gravitational forces can subtly modify Earth's orbital parameters over very long timescales, adding another layer of complexity to Milankovitch cycle predictions. Our galaxy's structure plays a crucial role in these orbital modifications. The plane of our solar system sits tilted at approximately 60 degrees relative to the galactic plane, creating a unique orientation that affects how external gravitational forces influence planetary orbits. As we move through different regions of the galaxy, the gravitational environment around our solar system changes in ways that can alter the timing and intensity of orbital cycles. Modern climate models now incorporate data about our galactic position and movement to improve long-term climate predictions. Scientists track our solar system's position relative to spiral arms, stellar associations, and other galactic features that could influence Earth's orbital dynamics and climate. This galactic perspective reveals that Earth's climate history reflects not just local orbital changes, but also our planet's journey through the dynamic galactic environment. These comprehensive models suggest that understanding Earth's true motion requires looking beyond simple orbital mechanics to consider our entire solar system's journey through space. The speeds and distances involved in this galactic voyage dwarf even the most extreme terrestrial velocities, creating a cosmic context that fundamentally changes how we perceive our planet's movement through the 220 kilometers per second. The scale of this galactic journey becomes clear when we examine the actual numbers behind our solar system's motion. While you sit reading this, your body travels through space at a velocity that would make a fighter jet look like it's standing still. Our entire solar system races through the Milky Way galaxy at approximately 227 kilometers per second. This speed represents one of the most staggering facts about our cosmic situation. Yet we feel absolutely none of this motion because we share the same reference frame as everything around us. Recent measurements have revealed that our solar system moves through the galaxy even faster than scientists previously calculated. Combining pulsar timing, Gaia's stellar motion, and Vera astrometry yields 227 kilometers per second around the galactic center, which translates to roughly 507,000 miles per hour. This updated figure represents a significant increase from earlier estimates and places our solar system among the fastest-moving stellar systems in our galactic neighborhood. The precision of these new measurements comes from years of careful observation using multiple independent techniques. These revised calculations also reveal that our solar system sits approximately 2,000 light-years closer to the galactic center than previous estimates suggested. This discovery emerged from the same observational campaigns that provided the updated velocity measurements. The combination of increased speed and reduced distance creates a more dynamic picture of our galactic environment, with stronger gravitational influences and more complex orbital mechanics than earlier models predicted. Scientists face enormous challenges when measuring velocities across such vast distances. Unlike measuring the speed of a car on a highway, determining our solar system's motion through the galaxy requires tracking our position relative to objects millions of light-years away. The European Space Agency's Gaia mission has mapped the positions and motions of over 1 billion stars, providing the most comprehensive dataset ever assembled for measuring galactic motion. By tracking stellar parallax measurements, astronomers can detect tiny shifts in star positions as our solar system moves through space. These parallax shifts are incredibly small, measured in milliarcseconds, but modern telescopes can detect them with extraordinary precision. Vera's radio interferometry provides another crucial measurement technique. This Japanese project uses multiple radio telescopes working together to achieve unprecedented precision in tracking celestial objects. By observing radio sources across the galaxy, Vera can measure our solar system's motion with accuracy that would have been impossible just decades ago. The combination of optical observations from Gaia and radio measurements from Vera creates a comprehensive picture of our galactic velocity. The measurements reveal that our solar system doesn't simply move in a straight line through the galaxy. Instead, we follow a complex orbital path around the galactic center while simultaneously moving up and down relative to the galactic plane. This three-dimensional motion creates a trajectory that carries us through different galactic environments over millions of years. The vertical component of our motion takes us approximately 7 kilometers per second away from the galactic plane, while we drift toward the galactic center at roughly 5 kilometers per second. A tremendous velocity means that we complete one full orbit around the galactic center in approximately 225 to 250 million years. This period, known as a galactic year, represents the time scale for our solar system's journey through the galaxy's major structural features. During each galactic year, we pass through spiral arms, traverse regions of varying stellar density, and encounter different concentrations of interstellar material. These environmental changes create cyclical patterns in the cosmic influences that affect our solar system. The speed at which we travel through the galaxy determines how quickly we encounter new cosmic environments. At 227 kilometers per second, our solar system moves fast enough to experience significant changes in galactic conditions over relatively short astronomical timescales. We traverse distances equivalent to several light years every 1,000 years, meaning that the cosmic environment around our solar system changes continuously as we race through different galactic regions. Our position within the galaxy also affects the types of cosmic influences we experience. The Orion Arm, where our solar system currently travels, represents a relatively minor spiral feature compared to the galaxy's major arms. This location provides a somewhat protected environment, with fewer massive stars and lower levels of dangerous radiation compared to the dense stellar population found in major spiral arms. However, our galactic orbit will eventually carry us through more active regions of the galaxy. At 227 kilometers per second, our solar system possesses enough velocity to circle Earth's equator in less than 3 minutes. This comparison helps illustrate the incredible speed at which we travel through space, carrying every atom on our planet along for this magnificent cosmic journey through the galaxy. Understanding our galactic velocity provides crucial context for interpreting many astronomical observations and determines the long-term evolution of our solar system's environment. Yet even these remarkable speeds and distances only tell part of the story about Earth's true motion through space. The path our planet actually traces as it combines orbital motion with galactic travel creates something far more complex than simple circular orbits around the Sun. The helical model revolution. Our solar system doesn't orbit alone. It follows a helical path through the galaxy. NASA and ESA research has revealed that when we combine Earth's orbital motion with our solar system's galactic velocity, our planet traces a massive spiral trajectory through three-dimensional space. This helical model represents a complete paradigm shift in how we visualize our cosmic motion, moving beyond the traditional view of circular orbits to acknowledge the dynamic, ever-changing nature of our journey through the galaxy. Traditional planetary models treat the Sun as a fixed reference point, showing planets orbiting in closed loops that repeat endlessly. However, this perspective ignores the crucial fact that the Sun itself races through the galaxy at tremendous speed. When we incorporate this galactic motion into our calculations, the closed orbital loops transform into open spirals that stretch across billions of kilometers of space. Earth's annual journey around the Sun becomes just one component of a much larger helical trajectory that carries us through different regions of the galaxy. Advanced computer models now incorporate precise measurements of the Sun's galactic velocity, planetary orbital mechanics, and gravitational interactions throughout the solar system. ESO animations demonstrate how Earth's helical path creates a spiral structure over 4 billion kilometers wide, with our planet following a corkscrew trajectory that combines orbital motion with galactic travel. The three-dimensional models show how Earth's path through space forms elegant loops that stack upon each other as we progress through the galaxy. These updated calculations account for the Sun's movement within the Milky Way, which directly influences Earth's trajectory through space. The helical model acknowledges that Earth's path depends not only on its orbit around the Sun, but also on the Sun's movement through the galaxy. This perspective reveals that Earth's journey represents a dynamic, ever-changing spiral influenced by galactic forces that extend far beyond our local solar system. The implications of this realization extend into every aspect of planetary science and astronomy. The spiral pattern created by our helical motion affects our exposure to cosmic environments in ways that scientists are only beginning to understand. As Earth traverses this massive spiral, we encounter different galactic regions with varying stellar densities, magnetic field strengths, and concentrations of interstellar material. These variations create cyclical patterns that may influence everything from atmospheric chemistry to long-term climate changes on Earth. Modern computer models can now track this complex three-dimensional motion with unprecedented accuracy. The simulations incorporate data from multiple astronomical surveys, including precise measurements of stellar positions, galactic structure, and cosmic motion. These models reveal that our helical trajectory follows predictable patterns that repeat over millions of years, allowing scientists to understand how our galactic position changes throughout cosmic time. The computational power required to model these interactions has only become available in recent years, enabling detailed analysis of our true cosmic motion. The helical path brings us through different galactic environments and cyclical patterns that affect our solar system's cosmic neighborhood. As we spiral through the galaxy, we pass through regions with varying concentrations of interstellar dust, different populations of nearby stars, and fluctuating levels of stellar radiation. These environmental changes occur on timescales ranging from millions to hundreds of millions of years, creating periodic variations in the cosmic influences that reach Earth. This model explains previously mysterious astronomical observations that seem disconnected from our local solar system dynamics. Cyclical patterns in Earth's geological record show correlations with our predicted position within the galactic spiral structure. The helical model provides a framework for understanding how our journey through different galactic regions might influence terrestrial processes through various cosmic mechanisms. The three-dimensional perspective reveals that Earth's orbit is tilted at approximately 60 degrees relative to the galactic plane, creating a unique orientation that affects how we experience galactic influences. This tilt means that our helical path carries us above and below the main disk of the galaxy in a complex oscillating pattern. The combination of our orbital motion around the Sun and this galactic oscillation creates a helical trajectory that exposes Earth to the full range of galactic environments over the course of our cosmic journey. Recent observations have refined our understanding of the solar system's position and velocity within the galaxy, providing more accurate data for helical path calculations. Scientists now place our solar system approximately 25,800 light-years from the galactic center, moving faster than previously calculated. This revised understanding of our galactic position and velocity provides crucial context for modeling our helical trajectory and predicting future cosmic influences on Earth. The scale of our helical path through space underscores the dynamic nature of our cosmic journey and the profound implications for understanding our place in the universe. The spiral structure spans distances that dwarf our solar system, highlighting how our planetary motion connects to the larger dynamics of galactic structure and evolution. This immense scale emphasizes that Earth's journey through space cannot be understood in isolation from the galactic context that shapes our cosmic environment. The helical model reveals that our solar system functions as an active participant in the galaxy's dynamic structure rather than an isolated system drifting through empty space. Our spiral trajectory carries us through the galaxy's spiral arms, between stellar associations and across regions with different physical properties. This journey through varying galactic environments creates complex patterns that define Earth's true path through space, and these patterns may have consequences that reach far beyond simple orbital mechanics, cosmic ray exposure, and genetic mutations. One consequence of our galactic journey involves exposure to high-energy particles from deep space that constantly bombard our planet as we race through different cosmic environments. These cosmic rays represent some of the most energetic particles in the universe, traveling at near light speed and carrying enough energy to penetrate Earth's atmosphere and magnetic field. Our position within the galaxy determines how much cosmic radiation reaches Earth's surface, creating variations in exposure that may influence atmospheric processes and climate patterns over long timescales. Recent research has established connections between cosmic ray exposure and atmospheric changes throughout Earth's history. Scientists studying a 2.5-million-year-old supernova explosion found evidence that this stellar death created a surge of radiation that reached our planet. The study, published in the Astrophysical Journal Letters, demonstrates how cosmic events can influence biological systems through increased radiation exposure. This finding represents direct evidence linking specific cosmic ray events to documented changes in Earth's environment, highlighting the relationship between galactic phenomena and terrestrial processes. As our solar system travels through different galactic regions, we encounter varying concentrations of high-energy particles from stellar explosions, stellar winds, and other cosmic sources. Dense regions of the galaxy, particularly spiral arms, contain higher concentrations of massive stars that produce more cosmic rays through their intense stellar activity and eventual supernova explosions. When our solar system passes through these regions, Earth experiences elevated levels of cosmic radiation that can persist for extended periods. The connection between galactic spiral arms and radiation exposure creates patterns that may correlate with changes in Earth's atmospheric and climate systems. Spiral arms contain active star-forming regions where massive stars burn through their nuclear fuel rapidly and explode as supernovas. These stellar explosions generate bursts of cosmic rays that propagate throughout the surrounding galactic region. When our solar system travels through or near spiral arms, we encounter these elevated radiation levels, creating periods of increased cosmic ray bombardment. Some work suggests cosmic ray flux, modulated by solar magnetic field and galactic position, may influence cloud formation, though climate impact remains debated. When high-energy particles collide with atmospheric gases, they create cascades of secondary particles including muons, electrons, and neutrons. These secondary particles may influence cloud formation by ionizing atmospheric molecules, creating charged particles that could act as cloud condensation nuclei. This process might affect global cloud cover patterns, which in turn could influence Earth's climate through changes in solar radiation reflection and heat retention. The atmospheric chemistry changes potentially caused by cosmic ray bombardment extend beyond cloud formation to affect fundamental chemical processes. Cosmic rays influence the formation of nitrogen oxides and ozone, which play crucial roles in atmospheric chemistry and climate regulation. Some studies suggest that cosmic ray variations might influence the development of weather systems, affecting regional climate patterns across the globe. These complex interactions demonstrate how cosmic radiation could create cascading effects throughout Earth's environmental systems. Approximately 14 million years ago, Earth's passage through the Radcliffe Wave, a large structure of gas and dust within the Milky Way's Orion arm, may have compressed the Sun's heliosphere. This compression allowed more interstellar dust to enter the solar system and reach Earth, potentially affecting the planet's climate and leaving its mark on geological records. This event coincides with the Middle Miocene disruption, a period of significant environmental changes, suggesting a possible link between galactic events and major shifts in Earth's atmospheric and climate systems. Predictions for future cosmic ray exposure depend on accurately tracking our solar system's path through the galaxy. Scientists can now model our helical trajectory through different galactic environments, identifying periods when we might encounter elevated radiation levels. These predictions suggest that our current position provides relatively moderate cosmic ray exposure compared to what we might experience in more active galactic regions. However, our galactic orbit will eventually carry us through different environments where cosmic ray bombardment could vary significantly. The helical motion of our solar system creates cyclical patterns in radiation exposure that operate over timescales of millions to hundreds of millions of years. As we spiral through the galaxy, we periodically encounter spiral arms, stellar associations, and other cosmic environments with different radiation characteristics. These cyclical exposures create rhythmic patterns in the cosmic influences affecting Earth, potentially contributing to some of the periodic patterns observed in climate changes and atmospheric variations throughout geological history. Current research efforts focus on developing more sophisticated models for monitoring cosmic ray effects on Earth's environment. Scientists are creating new detector systems and computational models designed to track atmospheric changes and climate patterns that may be influenced by cosmic radiation. These monitoring systems aim to distinguish between cosmic ray effects and other environmental influences, helping to clarify the role of galactic factors in Earth's atmospheric and climate systems. Understanding cosmic ray exposure patterns provides insights into how our galactic environment influences Earth's atmospheric processes and long-term climate evolution. By tracking our solar system's position within the galaxy and modeling cosmic ray exposure levels, scientists can better understand the complex relationships between our cosmic journey and terrestrial environmental changes. However, our movement through the galaxy involves more than just exposure to cosmic radiation, as our solar system follows a complex three-dimensional path that carries us through fundamentally different galactic environments. Galactic oscillation and mass extinctions. The vertical component of our galactic journey reveals another layer of complexity in our cosmic motion. Our solar system doesn't simply race through the galaxy in a straight line. Instead, we follow a complex three-dimensional path that carries us above and below the galaxy's main disk in a rhythmic oscillation that scientists are studying for its potential effects on Earth's environment. This vertical motion through the galactic plane creates cyclical exposure to different cosmic environments that may influence conditions on our planet. The galactic plane represents the densest part of the Milky Way, where most stars, gas clouds, and cosmic debris concentrate in a relatively thin disk. This region contains the highest concentrations of massive stars, stellar remnants, and active galactic processes that generate intense radiation and gravitational disturbances. When our solar system passes through or near this plane, we encounter dramatically different cosmic conditions compared to our current position above the galactic disk. The mechanism behind this oscillation involves complex gravitational interactions between our solar system and the galaxy's mass distribution. The galactic disk contains most of the galaxy's stellar mass, creating a gravitational field that acts like a cosmic spring. As our solar system moves away from the galactic plane, this gravitational force gradually slows our vertical motion and eventually pulls us back toward the disk. The process creates a regular up and down oscillation that carries us through different cosmic environments with predictable timing over approximately 60 million year cycles. Recent astronomical measurements have refined our understanding of this oscillation cycle using advanced computer modeling and observational data. Scientists can now track our solar system's vertical position relative to the galactic plane with unprecedented precision, revealing the complex dynamics that govern our three-dimensional path through the galaxy. These calculations show that our vertical motion follows predictable patterns that can be modeled and projected into the future. Passing through different regions of this oscillation cycle exposes Earth to varying levels of cosmic radiation and gravitational influences. The dense stellar environment near the galactic plane increases our exposure to cosmic rays from nearby stellar sources and creates different patterns of interstellar material that our solar system encounters. These environmental changes occur on timescales of millions of years, creating long-term variations in the cosmic influences affecting Earth's atmosphere and climate systems. Some researchers have hypothesized that this vertical oscillation may correlate with patterns in Earth's biological history, including mass extinction events. The Sheehan hypothesis suggests that our passage through different galactic environments could influence extinction rates through various cosmic mechanisms. However, the evidence for direct connections between galactic oscillation and specific extinction events remains inconclusive, and scientists continue to investigate these potential relationships. The pattern of our oscillation cycle affects our exposure to cosmic dangers in ways that scientists are still working to understand. Statistical analysis of extinction patterns in the fossil record shows some correlations with predicted oscillation timing, but establishing definitive causal relationships requires more research. The complexity of factors influencing biological evolution makes it challenging to isolate the specific effects of galactic position from other environmental influences. Computer models can now predict our solar system's future position within this oscillation cycle. These calculations incorporate our current position, velocity, and the gravitational influences that drive our vertical motion through the galaxy. The models reveal that our solar system reached its maximum distance below the galactic plane approximately 3 million years ago and has been moving upward ever since. This upward motion carries us away from the dense stellar environment near the galactic plane. Our current position above the galactic plane provides significant protection from many cosmic hazards. The reduced stellar density in this region means fewer nearby supernova explosions, lower cosmic ray exposure from local sources, and decreased gravitational perturbations from massive stellar objects. This position may contribute to the relatively stable cosmic environment that Earth has experienced during recent geological periods. The duration of this protective phase depends on the timing of our oscillation cycle and our current trajectory through the galaxy. Calculations show that we will continue moving away from the galactic plane for several more million years before our upward motion slows and eventually reverses. This extended period above the galactic plane provides Earth with millions of years of relative stability in terms of cosmic environmental conditions. Scientists can use models of galactic mechanics and oscillation timing to predict future changes in our cosmic environment. These predictions suggest that our solar system will eventually begin its descent back toward the galactic plane, potentially exposing Earth to different cosmic conditions. However, these changes occur over timescales of tens of millions of years, providing enormous lead time for understanding cosmic influences on planetary environments. Current measurements place our solar system approximately 82 light-years above the galactic plane and continuing to move away from this region. This position provides Earth with an extended period of relative protection from some cosmic hazards, offering stability for continued biological evolution. Yet our vertical position represents only one aspect of our location within the galaxy's complex structure, and our distance from other cosmic features plays equally important roles in determining relative to Sagittarius A star. At the heart of our galaxy lurks a monster so massive that it defies comprehension. Sagittarius A*, the supermassive black hole at the center of the Milky Way, contains the mass of 4 million suns compressed into a region smaller than our solar system. This gravitational behemoth controls the destiny of hundreds of billions of stars, including our own sun, as we orbit around it at incredible speeds. Recent measurements from the Gravity collaboration have now pinpointed our exact distance from this cosmic giant with unprecedented precision, revealing that we sit exactly 26,670 light-years away from the galactic center. This refined distance measurement represents a significant achievement in astronomical precision. The Gravity collaboration used advanced interferometry techniques to achieve an accuracy of 8.178 plus tilde minus 0.013 kiloparsecs, narrowing previous estimates that placed our solar system somewhere between 25,000 and 28,000 light-years from the galactic center. Scientists achieved this remarkable precision using coordinated observations from multiple telescopes working together to track the positions of stars near the galactic center. These techniques allow astronomers to create detailed maps of the galactic core region and determine our position within the galaxy's structure. The Event Horizon Telescope provided the first direct image of Sagittarius A in 2022, revealing the black hole shadow against the glowing material spiraling around it. This breakthrough imaging, combined with improved distance measurements, shows how this central monster actively shapes our galactic environment. The black hole continuously consumes surrounding gas and dust, releasing tremendous amounts of energy that influence stellar formation and galactic dynamics across vast distances. The accretion disk around Sagittarius A glows with temperatures exceeding billions of degrees, creating one of the most energetic environments in our galaxy. Our specific distance from this galactic center determines fundamental characteristics of our solar system's orbit and long-term stability. The gravitational influence of Sagittarius A* creates the circular velocity that carries our solar system around the galaxy at approximately 227 kilometers per second. This orbital speed depends directly on our distance from the galactic center. Following the same gravitational principles that govern planetary motion around the Sun, stars closer to the galactic center orbit faster, while those farther away move more slowly through their galactic orbits. The gravitational effects from the galactic center extend far beyond simple orbital mechanics. Gravitational waves generated by the interactions of massive objects near Sagittarius, the asterisk, propagate throughout the galaxy at the speed of light. These waves create tiny distortions in space-time that advanced detectors can measure, providing information about the violent processes occurring in the galactic core. The waves carry energy that can influence stellar dynamics and potentially affect the orbits of objects throughout our solar system over very long timescales. If our solar system were positioned significantly closer to the galactic center, the consequences for Earth would be catastrophic. The intense radiation environment near Sagittarius A** would strip away our atmosphere and sterilize the planet's surface. High-energy particles from the accretion disk would bombard our solar system with lethal doses of radiation. The stronger gravitational field would also increase the orbital speed of our solar system, potentially disrupting the delicate gravitational balance that maintains stable planetary orbits around the Sun. Conversely, positioning our solar system much farther from the galactic center would create different problems for habitability. The outer regions of the galaxy contain fewer heavy elements necessary for rocky planet formation and biological processes. Stars in the galactic halo and outer disk form from primordial gas that lack the carbon, oxygen, silicon, and iron that comprise terrestrial planets. These outer regions also experience less stellar recycling, the process by which dying stars distribute heavy elements throughout the galactic environment. Our current position represents what astronomers call the galactic habitable zone, a region where conditions optimize the potential for life to develop and persist. This zone extends roughly from 22,000 to 29,000 light-years from the galactic center, encompassing the area where heavy element abundances support rocky planet formation while avoiding the intense radiation and gravitational disruption of the inner galaxy. The zone also corresponds to regions where spiral density waves create appropriate levels of stellar formation without triggering excessive supernova activity. The concept of galactic habitability extends beyond simple distance from the center. Our position within the Orion Arm, a minor spiral feature, provides additional advantages for life. Major spiral arms contain higher concentrations of massive stars that undergo supernova explosions more frequently. These stellar deaths release intense bursts of radiation that can cause mass extinctions on nearby planets. Our location between major spiral arms offers protection from these dangerous stellar processes while maintaining access to the heavy elements distributed by previous generations of stars. The precise measurement placing us exactly 26,670 light-years from Sagittarius. Its star confirms that our solar system occupies an optimal zone for planetary stability within our galaxy. This distance provides the perfect balance between access to heavy elements necessary for life and protection from the deadly radiation and gravitational forces that dominate the galactic center. Yet our favorable galactic address represents only one factor in the complex web of cosmic influences that shape conditions on Earth. The environmental consequences of our cosmic journey extend into realms that scientists are only beginning to understand: climate patterns and galactic influence. Research connecting our galactic position to Earth's climate systems reveals mechanisms that could fundamentally change how we understand weather patterns and long-term climate cycles. Scientists studying the relationship between cosmic rays and atmospheric processes have identified pathways through which our journey through the galaxy influences conditions on our planet. These cosmic influences represent one of many factors under investigation that may help explain climate phenomena that traditional terrestrial models struggle to address completely. The connection between galactic cosmic rays and cloud formation represents one of the most intriguing discoveries in recent climate research. When cosmic rays enter Earth's atmosphere, they collide with gas molecules and create cascades of secondary particles. These secondary particles carry electrical charges that influence the formation of cloud condensation nuclei, the tiny particles around which water droplets form in the atmosphere. Tinsley's work on ionization and clouds suggests that cosmic ray variations can affect cloud properties, though the estimated effects remain modest compared to other climate drivers. Cloud cover plays a critical role in regulating Earth's temperature by reflecting sunlight back to space. Even small changes in global cloud coverage can create measurable shifts in how much solar energy reaches Earth's surface. When cosmic ray intensity increases, the enhanced ionization can influence cloud formation processes under certain atmospheric conditions. Conversely, reduced cosmic ray bombardment might lead to different cloud formation patterns. This mechanism provides a potential pathway for galactic influences to affect Earth's climate alongside solar cycles, volcanic activity, and human factors. Our helical path through space creates predictable patterns in cosmic ray exposure that operate over millions of years. As our solar system spirals through the galaxy, we encounter regions with different stellar densities, magnetic field strengths, and concentrations of high-energy particles. These galactic environments change our exposure to cosmic radiation in cyclical patterns that may contribute to long-term climate variations on Earth. The helical motion means that cosmic influences on our climate follow regular cycles linked to our position within galactic structures. The timing of ice ages shows correlations with our predicted galactic position throughout Earth's history that scientists continue to investigate. Major glacial periods appear to coincide with times when our solar system passed through regions of potentially elevated cosmic ray exposure. The enhanced cosmic radiation during these periods may have influenced cloud formation and atmospheric processes enough to contribute to temperature changes that supported ice sheet expansion. This connection suggests that our galactic journey may represent one factor in the complex web of influences that drive ice age cycles. Scientists are incorporating cosmic ray data into climate models with increasing sophistication. Current research uses detailed maps of galactic structure and our solar system's trajectory to predict future cosmic ray exposure levels. These models account for our movement through spiral arms, between stellar associations, and across regions with different magnetic field configurations. By understanding how these cosmic environments change over time, researchers can anticipate periods of elevated or reduced cosmic ray bombardment and their potential atmospheric effects. The interaction between galactic influences and human-caused climate change creates complex scenarios that challenge existing climate models. While human activities increase atmospheric greenhouse gas concentrations, cosmic ray variations operate through different mechanisms involving atmospheric ionization and cloud formation processes. These climate drivers may sometimes work in complementary or opposing directions, with cosmic influences potentially modifying the atmospheric conditions that determine how greenhouse gases affect global temperatures. Climate scientists must consider how cosmic ray variations might interact with rising carbon dioxide levels and other anthropogenic climate factors. During periods of high cosmic ray exposure, changes in atmospheric ionization might influence cloud properties in ways that affect how much solar radiation reaches Earth's surface. However, during periods of low cosmic ray bombardment, different atmospheric conditions could modify how greenhouse gases interact with incoming solar energy. Understanding these interactions becomes important for comprehensive climate predictions. The possibility that galactic influences represent a missing piece in climate science could help explain phenomena that remain incompletely understood through terrestrial factors alone. Long-term climate variations, certain aspects of ice age timing, and patterns in paleoclimate records might become clearer when viewed through the lens of our galactic journey. This cosmic perspective could provide additional context needed to understand Earth's complete climate history and the multiple factors that shape atmospheric conditions over different timescales. Current research focuses on quantifying how galactic cosmic ray variations affect atmospheric processes and cloud properties. The measurements require sophisticated monitoring systems that can distinguish between cosmic ray effects and other influences on atmospheric chemistry. Scientists use particle detectors, satellite observations, and atmospheric models to track how cosmic ray intensity correlates with cloud characteristics across different regions and time periods. The precision of these measurements continues to improve as new monitoring technologies become available. Advanced satellite systems can detect changes in cloud cover patterns that may correlate with cosmic ray variations. Ground-based detectors track cosmic ray intensity with unprecedented accuracy, providing data needed to establish connections between galactic influences and atmospheric processes. These technological advances make it possible to study cosmic climate effects that were previously difficult to measure reliably. Studies indicate that galactic cosmic ray variations can affect global cloud cover by measurable amounts, creating atmospheric changes that influence regional climate patterns. This finding establishes cosmic ray bombardment as one climate factor that operates alongside other influences to shape Earth's atmospheric conditions across multiple timescales. The growing understanding of these cosmic connections provides scientists with new tools for analyzing Earth's climate system and the complex interplay of factors that determine our planet's environmental future. Predicting the future through cosmic motion. Understanding our true cosmic motion through the galaxy provides humanity with unprecedented insight into Earth's future environmental conditions. This knowledge transforms us from passive observers of cosmic events into informed participants who can anticipate and prepare for changes that will affect our planet across extended timescales. The ability to predict cosmic influences on Earth represents a fundamental shift in how we approach long-term planning and our relationship with the universe itself. The potential for preparing humanity for cosmic-scale changes becomes real when we understand the predictable patterns in our galactic journey. Unlike random catastrophic events that strike without warning, the cosmic influences driven by our solar system's motion through the galaxy follow mathematical patterns that we can calculate well in advance. This predictability means that future generations could receive detailed warnings about approaching cosmic environmental changes, providing time to develop protective technologies or adaptation strategies. Computer models now incorporate the complete picture of our galactic journey into long-term environmental predictions. These sophisticated simulations combine data about our helical path through space, cosmic ray exposure patterns, gravitational influences from galactic structures, and oscillations through the galactic plane. The computational power required to process these complex interactions enables scientists to create comprehensive models of how cosmic motion affects planetary conditions over predictable cycles. These cosmic predictions could revolutionize space exploration strategies by identifying optimal timing for missions and understanding long-term environmental trends. Periods of cosmic stability provide valuable information for planning human expansion beyond our planet, while dangerous periods might require enhanced protection or modified mission parameters. Understanding when Earth will face increased cosmic radiation helps inform decisions about space-based infrastructure and planetary protection systems. Planetary defense strategies benefit enormously from understanding our cosmic motion and its effects on objects throughout the solar system. The gravitational perturbations caused by our passage through different galactic regions can alter the orbits of asteroids and comets over extended periods. By tracking our galactic position and modeling these gravitational influences, scientists can identify periods of potentially increased impact risk and develop appropriate monitoring systems. Our cosmic motion understanding becomes essential for long-term environmental planning because it reveals the ultimate constraints that govern conditions on Earth. While human activities currently dominate discussions about planetary environmental change, cosmic influences operate on much larger scales and longer timescales. Understanding these cosmic factors provides crucial context for interpreting Earth's environmental history and anticipating future changes that extend beyond terrestrial influences. The search for other cosmic influences becomes more systematic when guided by our understanding of galactic motion. Scientists can now identify specific galactic regions and stellar environments that our solar system will encounter, allowing targeted research into the cosmic phenomena we might experience. This approach could reveal previously unknown cosmic influences that affect planetary environments and our biological systems in ways we haven't yet fully understood. Our galactic journey exposes Earth to varying cosmic environments that create cyclical patterns in radiation exposure and gravitational influences. These patterns operate over millions of years, creating periodic changes in the cosmic conditions that affect our planet. Understanding these cycles provides insight into long-term environmental variations that may influence climate systems, atmospheric chemistry, and biological evolution across geological timescales. The cosmic motion perspective reveals that Earth's environmental history represents one chapter in a much larger story of galactic interaction and cosmic evolution. The conditions that allowed life to develop on our planet result from our specific trajectory through galactic space and the cosmic influences we encountered along the way. Understanding this cosmic context becomes crucial for interpreting Earth's biological history and predicting future evolutionary pressures. Future technological development could incorporate cosmic motion predictions into design principles for long-term infrastructure and environmental monitoring systems. Energy systems, communication networks, and environmental protection technologies might be designed to function effectively during periods of varying cosmic radiation or gravitational influence. This approach would create human systems that remain functional across the range of cosmic environments our planet encounters during its galactic journey. The integration of cosmic motion understanding into human knowledge systems represents a significant advancement in our species' intellectual development. This knowledge connects local planetary phenomena to galactic-scale processes, revealing the cosmic context that shapes our existence. The ability to predict cosmic influences provides valuable foresight into our planet's future environmental conditions and the factors that will influence biological evolution. Current models demonstrate that we can predict cosmic influences on Earth across multiple cycles of our galactic journey, providing humanity with unprecedented insight into our planet's cosmic environment and the periodic changes that will shape our species' long-term relationship with the universe. This knowledge reveals patterns and connections that extend far beyond what previous generations could have imagined, fundamentally changing how we understand our place in the cosmic order and the forces that determine our planetary destiny. These discoveries establish a foundation for understanding our cosmic environment and its influence on planetary conditions. By expanding our reference frame from sun-centered to a galactic perspective, we see Earth's path as a helical spiral at 227 kilometers per second, shaped by orbital and galactic motions. This deeper view reframes everything about motion, climate, and cosmic influence on our planet. The knowledge that we participate in this cosmic dance while experiencing none of its motion demonstrates the profound nature of relative motion and our place within galactic structures. Every moment of your existence occurs while traveling through space at tremendous speeds, making us all participants in an incredible journey through the Milky Way galaxy that connects local planetary processes to cosmic scale phenomena across vast distances and timescales.